I'm Michelle Sterling for Friends of Science Society. I'm here in Porto, Portugal for the Basic Climate Science Conference that was just held at the University of Porto.
So I will present one of my latest papers, but I also will tell you something about the future, so what I am working right now. Okay, so I will show you some results that has not been published yet, but I think that is quite interesting. Now, first of all, let us talk about these things. So we have, somebody have talked about the length of the day, the importance of studying the length of the day, so the rotation of the Earth, and we have here that LOD is actually closely linked to variation in climate, so in particular to the North Atlantic Oscillation, to the global surface temperature, and so on. So we will study LOD, and we will compare it with the North Atlantic Oscillation and with its generalization, that is a zonal index. That is, so now is one part, it can be considered a subset of the Zola index, so we will talk it in one moment. And the results that I would like to show in this first part of my talk is that actually this index would suggest that during the Maunder minimum, so the Little Ice Age, the temperature could have been about 1 degree cooler than this period. So it's relatively cold, And I will explain you the importance of this kind of finding. And then I will discuss about the cycles that we have talked about. So, for example, the 60-year cycle and others, many other cycles, but I will focus on the 60 and 1,000-year cycle. Now, these are the data that we are talking about. This is the length of the day. This is a reconstruction North Atlantic Oscillation. This is the global surface temperature of the ocean. And this is the zonal index, that is a difference of pressure between these two regions, right? These two regions here. And you see here that this difference of pressure during these two regions show a very strong oscillation. So this is 60 years oscillation that actually we found also here, we found here, okay, we found here, and so on. So these things are related to each other. Now, when we talk about the zonal index, we need to realize that the wind, essentially, the current here, moves, oscillate in a different way. Okay, so we have the zonal flow, so we have this movement. Okay, so when the zonal index is high, essentially we have this kind of situation. When the zonal index is low, we have this kind of movement, and these are different because essentially when these things like this, there is a small oscillation, there is a small oscillation here. It's more difficult for the heat from the equator to move north. Okay, so these things cools down, and instead when there is like this, it's easier for hot weather to go north. So we have a difference between this situation. There is a continuous oscillation between this and this situation, and there are periods when this pattern is prevalent and this pattern is prevalent. Now there is some equation that we can use to study this movement. Actually, it's possible to demonstrate that if these things is true, no? So we can actually define some other index. So this is integral zeta index. So it's an integration of the zeta I and the integral North Atlantic Oscillation, that is an integration of these things. It's possible to use some basic physics to demonstrate that this relation should hold if these things are correct. So essentially E zeta E should be more or less is proportional to E now, and this would be proportional to minus length of the day. So there is a negative correlation between LOD and E now and EZ. And then so it will be equivalent to these things too. So now SST and minus LAD. So there is this kind of correlation. So this would be the case if something is driving climate change, something from outside the Earth, for example, this external torque, which then alters LOD, so it creates this kind of pattern. Of course, people also say that the oscillations that we find in the climate are all internal to the Earth system, right? So internal to the Earth system necessarily, so physics tell us that if everything happens to something internal to the solar system, the angular momentum of the system should be conserved. If this is the case, the relation should be this one. So zeta I should be actually proportional to LAOD. So we have these two things, okay? So we have this relation here, one case, internal dynamics only, or dynamics driven by external forcing, external torque. So there is a very different relation. So we can check one of the two by looking at the data. And these are the data. So this is a difference between LOD and E zeta E. So you see that there is a perfect anti-correlation. It's a perfect anti-correlation. So it's a first case. This is the relation with SST, LOD SST, and we see again there is a E zeta E goes like minus LOD. There is a perfect anti-correlation. And again, this is a relation with LOD, and now again we have a perfect anti-correlation. It's pretty good. So we deduce that we can exclude that climate change, this oscillation that we observe in the climate, is due to internal variability of the climate system. There must be external forcing. There must be an external forcing which is driven this oscillation, okay? So external forcing, we do not know what yet. So solar force is something, lunar something, but must be external, it cannot be internal, because internal should have been a different relation between the data. And then we can use these correlations between very strong correlation that we found, and we can extrapolate in the past. So now it's very long index, LOD is very long index, and assuming that the surface temperature of the ocean is what indicates the climate temperature, real climate temperature, assuming this is variation is due to this, is coupled to this variation in LOD and in now. Then we found out, we can extrapolate in the past, and we found out that the temperature during the modern mean little ice age should have been about a little bit more than 1 degree cooler than during this period, okay, so recent period. So it's a relatively cold period. This pattern actually is found in some boreal records, so that they show that the temperature during the modern minimum could have been around 1 degree, 1.5 degree cooler than modern time. And actually, there is a lot of reconstruction of global surface temperature. And here it's important to notice that so here there is not the hockey stick, okay? The hockey stick, you remember the hockey stick, right? The hockey stick said that the pre-industrial climate is practically constant. The hockey stick, which is not present in this graph because it's been already completely debunked, essentially is what has convinced the people around 2000 that the climate models based on CO2 could be right, because those models show that not much variability during this period, okay? Instead now, a lot of people claim that there is a variability, large millennial variability in the climate system, somebody a little bit less, somebody a little bit more, but we see that there is this variability. And, yeah, tell me. And here in this graph, you can see the difference between essentially a reconstruction, so it's an empirical model that simulates the climate model of the IPCC extrapolated in the past during 1,000 years. So essentially all these models essentially reproduce a hockey stick pattern, because they assume that the sun is practically zero, so practically does not gives any effect, and all effect is given by CO2 and volcano, and during this period the CO2 is relatively flat, so the models produce some flat records. But these things here seems to fit well, but fail completely to reconstruct the medieval warm period. So we have centuries of failure, okay? Centuries of failure. So these models of the IPCC are completely inconsistent with the medieval warm period, because they would be a big difference. The only way to get the medieval warm period is to increase the solar effect on climate by many times, 3, 4, 5 times more than what the IPCC claims. It's necessary to use other different kind of total solar irradiance models than this one that they are using. They are using a total solar irradiance model that practically does not have any variability. So we need, there is a lot of work. But essentially we get this kind of it's possible to reconstruct the temperature by assuming a very strong solar effect on climate and reducing the anthropogenic forcing at least by factor of 2. At least, so that means that the climate sensitivity must be around 1.5 at most. That is my upper limit, okay? And then, okay, so these models, I don't talk much about these models. These are based on specific oscillations that I identified, but I will talk later in one moment. So what can we do about these things? So the idea is that this is a reconstruction of total solar irradiance. It's the HOI reconstruction plus the ACRIM data here. They fit relatively well the temperature from central England. Okay, this is a central England temperature. So this is this is very long record. So we see pretty well this correlation. This is some reconstruction of temperature in the northern region. So you see that there is a fitting, very, very good fitting here. So what can we say from this? The fact is that bigger is this cycle, okay, and the bigger is the solar activity effect on the climate, and smaller must be the effect of CO2. Okay, so because the sun must be always the same. Okay, so that is the first thing. The new reconstruction show a very large variability, pre-industrial variability, which means a very strong solar effect on climate, and simultaneously we need to conclude that the effect of CO2 must be reduced, can be at least by half. This is another record, 10,000 years record, is solar activity against climate in one region in China. You see that the correlation between the two continues for forever, essentially. So it's always the sun that drives climate change. And in this record, you don't see well, but there is a 1,000-year cycle included in this record. So practically there is these cycles that you see here is just 1,000-year cycle, 1, 2. So you see 1,000-year cycle in that is repeated for 10,000 years more or less. Yes. And we have seen this before, so there is a tendency now in considering that the climate sensitivity of CO2 is significantly smaller than what the models adopted by the IPCC show, at least half. Now we are around at least 1.5, okay? This is my prediction made several years ago. It's a forecasting, my forecasting made several years ago. So when I do the first kind of model that I produced in 2009 was here. So then the data were here. Now we are here. Notice this peak. This peak is the hottest here of the record, but it was just El Niño peak, okay? So there are papers published that confused this peak for anthropogenic warming, so they said that the climate models were validated by the data, but then the temperature went down, and they are still following my model. This is always my model, so we have from here to here. So these are the climate model of the IPCC. This is a model based on specific cycles, including the 60-year cycle, and the 1,000-year cycle, and then there is a 20-year cycles, and then there are 10-year cycles, and so on. So, and the models plus a signal from anthropogenic forces. But now I would like to explain you the origin of these cycles. I will focus only on two cycles: the 60-year cycles that people have talked a lot, and the 1,000-year cycles. And where can we find it? Now I will show you something new, never published. Wow, what is this? This curve that you see here is the variation of the eccentricity of the orbit of Jupiter. So the orbit of Jupiter is not stationary, it's varying in this way. And this is the variation of the eccentricity of the orbit of Saturn. Okay? So, what is this? You see here, this oscillation here. What is this oscillation here? Is this? Is a zoom. This is 60-year cycle. This 60-year cycle. And then you get this oscillation here. This oscillation here. This is a 900, 1,000-year cycle. Okay? Now let us see how they compare against the data. This is the 1,000-year cycle of the eccentricity of Jupiter. This is the global climate record, temperature record for linguists. So you see here, this 50. This is 60-year cycle against, this is the Indian monsoon record. This is the global temperature record. I took off the warming. Okay. This is so this is one index of North. What is it? So it's North Atlantic Oscillation. No, it's Atlantic Oscillation. This one. Yeah, and you see here these are several centuries, and we get a very nice matching. I am not changing the phase of this cycle, the 60-year cycle. It's exactly the 60-year cycle that you have seen in the original record, okay? Of this record here, of this record here. So this is a variation of the oscillation. And now, well, I would like that you focus on this picture. I do not know if this is clear. Now, this is Jupiter orbit. This is Jupiter orbit. These are the orbit of the planets, internal planets of the system. What you see here are the asteroids, okay? The orbit of the asteroids. So these are the Trojan asteroids in the Lagrangian point of Jupiter that are nearly stable. But then you have the asteroids of the asteroid belt, okay? So you see here that there is a huge dynamics that is driven by Jupiter. Jupiter is driving, is forcing all these particles, there are thousands of particles, asteroids, moving in this region in a very complex way. You see that it's not a circular orbit, it's a kind of triangular orbit, okay? It's a kind of triangular orbit, so it's a very, very complex way. Now, the eccentricity of Jupiter is not constant, as we have seen before. The eccentricity of Jupiter is varying with a 60-year cycle and with a 1,000-year cycle. And this area, this region is varying with that period, okay? Sometimes it's more compressed, sometimes it's more circular, sometimes more compressed. So there is this bunging, these things, and these things very likely alters the dynamics of the asteroids here, okay, and everything that is here, dust and so on, and the Earth is here. So very likely there is here a variation of the dust. There might be a variation of the dust and of the other particles falling on Earth that is following these 60-year cycle, 1,000-year cycles linked to the eccentricity of these things. So the solar system is pulsing because with these cycles, and probably there is something happening at the level of the Earth, for example, dust coming in the Earth and influencing the electric field inside this region that also influences the solar activity. So there is a lot of change in that things. And this is my conclusion. So practically what is happening here is that the period of the planets very likely is driven solar system. So this is what is the machine. This is changing solar activity, is changing everything inside the solar system with that frequencies. And this, of course, then end up to influence also the space environment of the Earth, and therefore also the climate of the Earth, because in particular for cloud system, a cloud system forcing, direct forcing of the cloud system via dust, via electric particles, via solar activity that has been influenced by the planets and so on. And so this is my